introduction to large deviations for Markov processes. So I want to discuss a bit the spectral problem, and then I want to show an example where we applied everything that we discussed yesterday, and that will close the first lecture, which is now the second. And then in the second part, then I'll discuss this prediction problem to try to explain how fluctuations arise dynamically in time. Okay, so here I've put a summary of what we had yesterday. So we have a Markov process over a time horizon 0 capital T. Over that time horizon, we define some random variable AT, where after the large deviation principle ruling the distribution of that random variable, and so we want to calculate the rate function here, I of A. And then using the Gartner-Ellis theorem, we're going to extract the rate function as a Legendre transform of some function lambda k, which is the scale cumulative generating function. And then for a Markov process, this, under some condition, is the principal eigenvalue of some modified generator of the process. And so what we have to now solve is a spectral problem to extract this dominant eigenvalue, this principal eigenvalue, for the linear operator Lk there. Okay, I'm not writing the expression of Lk, something that I wrote yesterday. So now I want to discuss the spectral problem, how we actually solve this and extract the dominant eigenvalue, and what we can say in general about this spectral problem. Okay. So this is where I start now. So the spectral problem. So essentially for this, there's an easy case and there's a difficult case. Okay. The first case I'll call equilibrium. I'll start with this. So suppose you start with a process which is reversible. So from a physics point of view, you would call this an equilibrium process. And then you have to have also that G, the G function. So remember, my observable will involve two functions, f and g. So there's a time-integrated part involving f, and there's a current part involving g. So if g is gradient, and f is arbitrary, so any f actually will do in this case, then what you can show here is that the Lk that I had has a real spectrum. Okay, so although L itself is not emission and Lk won't be emission, it has a real spectrum. So it's conjugated to a Hermitian operator, and as a transformation, there should be a unitary transformation that takes you from Lk to another Hermitian operator, and then we'll call this a symmetrization, and then we can build that symmetrization explicitly. And this is the easy case, because after the symmetrization, we have a Hermitian operator that looks very much like a Schrödinger operator. So like we need to solve a quantum type problem, and this is something that we know a lot about, so we can do something here to extract the dominant eigenvalue, which for the quantum problem will correspond to a ground state. Okay, and then the example will show this exactly. So this is the easy case where now you have a real spectrum, and then you can map this to a quantum problem. So can be mapped to a quantum problem. And so we know a lot about the spectrum of Hermitian operators, about spectrum of quantum-like systems, and this is something that we can use to our advantage to get the dominant eigenvalue. The difficult part is when you're dealing with non-equilibrium system. So in this case, if you start with a system for which you know you have a non-reversible system, or if you're dealing with a reversible system but you have a G that's not gradient, you'll still be on the difficult side of things. And then F again is arbitrary. So F doesn't play any role actually in the difficulty of the spectral problem that you have to solve. Then here you're going to have that in general Lk has a complex spectrum. Okay, the dominant eigenvalue will be real, but you have a complex spectrum, which means that you cannot map that problem into a quantum problem now. There's no Newtonian transformation that will map this operator to a Hermitian operator because it contradicts the fact that this has a complex spectrum. Okay, so here no mapping to the quantum problem. So if you remember what I was discussing yesterday, in order to solve this spectral problem, you not only have to consider that direct spectral problem, but you have to consider the dual too, and then actually deal with the boundary condition involving the R and the L, so the direct eigenfunction, but also the dual eigenfunction. And that makes the problem just so much more complicated. Whereas for this one, since you're mapping to a quantum problem, you only have to solve one spectral problem, which is the emission problem that you would solve in quantum mechanics. Yes? You'll see this because if you remember in the LK, we had terms like this. And if you have a G gradient, you can absorb now the gradient as a new gradient, and it keeps the spectrum. You can show that if G is gradient, it doesn't change the spectrum of L. So if you start with reversible, and then you have a gradient G, you keep the realness of the spectrum, whereas if G is not gradient, you lose this. Okay, and then from a physical point of view, this is related to having a current in the system. And I think it will become clearer in the second part of the lecture when I discuss how fluctuations are created. If you have a G that's not gradient, this means essentially that you're asking for currents to be created in the system, and that becomes non-equilibrium. Okay, so you can start with a reversible system, but if you're looking for current fluctuations, the system will be acting in a non-equilibrium way to create those fluctuations. And inherently, you're dealing with a non-reversible system. Okay? Okay, so that's a very crude classification, but from the practical point of view, when you want to solve a problem, this is what you're faced with. Equilibrium versus non-equilibrium. But again, the non-equilibrium part is not only defined by xt, but also by the nature of G, because now you're looking at fluctuations, not just at the system itself, but how the fluctuations are created. And again, we'll see this very clearly in the second part. So now what I want to do, and this will finish the lecture, is that I want to show you an example of this side, what we do here, and then I want to show you what the symmetrization here is from reversible, from a non-emission operator to an emission operator. So this is the symmetrization. So this is something that's known. You can do this for jump processes. You can do this also for Markov chains. And so I'll show this for diffusion. I'll look for a specific diffusion, so a very easy case where you have the sigma is proportional to the identity matrix. So essentially you have the same temperature in all the noise components. And then you have a gradient drift. And so that's a gradient system. That's a purely gradient system. We know that system is reversible. And so the stationary density, in this case, I wrote it yesterday, but it's a Gibbs state to potential divided by the noise power epsilon squared. Okay, I'm not going to derive the whole symmetrization. I'm just going to write down what the symmetrization is. So you start with your non-emission operator, and then you're going to transform this into emission operator, and the transformation is the following. You take the stationary distribution on one side, just sandwich it like this, okay? An operator sense. So if you imagine this acting on some function, you would put the function here, so L is acting on the product here, not just on the PS on that side. Okay, this is a well-known transformation in physics as a symmetrization. The outcome of this, if you write down actually the action over a test function, is that you'll end up with the Laplacian minus some function of x here, which is an effective potential for a Schrödinger problem. And the potential is written explicitly as gradient of the potential squared over 2 epsilon squared minus the Laplacian of your potential divided by 2 minus kf. Okay, I have x everywhere here. So this is just a function. And this is an effective, if you look at this, this is a Schrödinger operator. You have a Laplacian minus a potential. Okay, compared to the quantum problem, actually there's a minus sign difference. In quantum mechanics, you have a minus sign here, you have h bar. So the role of h bar here is the noise power. mass is equal to 1, and then you have a potential, a VK here. So that's the effective potential for the quantum problem. So you're solving a particle in a potential VK. This is what you're doing. And if you put the minus sign correctly in there, then the dominant value that we want to find for LK is also the dominant eigenvalue of HK. And then with the minus sign, that corresponds to the ground state of your quantum system. So we have to solve a quantum system, extract the ground state, and that's it. And this is now, the ground state will be a function of K, okay? Oh, yeah, sorry, so here I forgot, G is equal to 0. I'm not putting, for simplicity, I'm not putting any G. But if you have a G gradient, then you can also do a bit of calculation, and then you get also to this kind of symmetrization. Okay, so here I have a pure F observable, so it's purely additive in time, and then you can do this for any F. Okay, so what I'll do is that I'll just apply this very quickly to an example, which is actually part of the lecture notes, but I'll just go very quickly on this. And then you have more examples as exercises in the lecture notes. So from very easy, like a kind of slight generalization of the problem I'll be talking about now, to very difficult problems that are actually open problems. And then you see this in the rating. I have ratings. I'm rating the exercises according to Knuth logarithmic scales of rating exercises. So you have 0, 10, 20, 30, 40, but 40 is not just 4 times the difficulty of the first one, it's actually logarithmic. So you have to think about this. Okay, so the example is the Ornstein-Uhlenbeck process. Ornstein-Uhlenbeck. So it's the linear diffusion. I take this for simplicity to be the one-dimensional case. So I have minus gamma xt dt plus sigma, and then my Wiener increment, the Gaussian white noise. So I have sigma strictly greater than 0, and I have the gamma also like this, and the state itself is one-dimensional. Okay, just in R. So here I can define many observable. The one I'll be considering is just the integral of the state itself. So if you think about it, this is the area under the path of the Ornstein-Uhlenbeck process. Okay, so that's the area per unit time. So if I look at trajectory, I can have something like this for my Ornstein-Uhlenbeck up to some time capital T. And then I just look at the area fluctuations of Ornstein-Uhlenbeck divided by T. Okay, here if you know anything about Gaussian processes, you can guess the rate function, because this is a Gaussian, this is a linear process, this is a linear transformation of the Gaussian white noise. So this is a Gaussian process. The integral of a Gaussian process is also Gaussian. So the fluctuations of the observable are Gaussian, so the rate function will be a quadratic. Okay, but I just want to go over now the full large deviation calculation to confirm this. Okay, so the steps now is like this. So what I need to do is to define my tilted generator, and I need to find the dominant eigenvalue of this. So the first thing I write here is to say, okay, what is my F? What is my, okay, so first maybe the capital F, I can extract everything, linear force, that's good. I have my sigma, this is for the process. Then for the observable, I see that the small f will just be the linear function, and g is equal to 0. So now I have a gradient system with a pure f observable, so I know I'm in the reversible case, so I can do a symmetrization, and indeed I'll be doing this. So my tilted generator in this case is L plus kf, so that's the f derivative plus sigma second derivative, that's the Laplacian, plus kf, and there I can replace the capital F by minus gamma x. Okay, so this is obviously non-emission, but I can do a symmetrization. If I do the symmetrization, then I get sigma squared over 2 second derivative. So the symmetrization, the effect of the symmetrization, if you think about it, is to kill the non-emission term in the generator. So here, this is the part, so the symmetrization will just cancel this part, and then we'll retain this part, and it's adding now a potential as it kills the derivative part. Okay, so here I have this, and the potential is minus gamma squared x2 divided by 2 sigma squared plus gamma 2 plus kx. Okay, so this is my vkx here. Now you see that the potential, the effective potential, is a parabola. So what I'm dealing with effectively is the quantum problem, I need to find the spectrum of the quantum harmonic oscillator. Well known, of course. So I can just use what we know from quantum mechanics. And what you find is that the ground state, in this case, is a quadratic. It's sigma squared k squared over 2 gamma squared. This is a parabola. Now I need to use the Gardner-Ellis theorem to get the right function. This is differentiable in K, so I can take the Legendre transform of this. The Legendre transform of a parabola is a parabola. So the parabola is the fixed point, is a fixed point of the Legendre transform, but in fact it's the fixed point of the Legendre transform. So after Legendre transform, so from the Gardner-Ellis theorem, I get that the right function is indeed a parabola. It's gamma squared, a squared over 2 sigma squared. Okay, so Gaussian fluctuations. Okay, so this is the kind of calculation that you'll do for other observables, for other processes, if they fall into the category of problems that you can symmetrize. As an exercise, you can generalize that problem by looking at the integral of x squared. This is a slightly more difficult problem, but it also maps to the quantum harmonic oscillator. In this case, the rate function is not a parabola, so you have non-Gaussian fluctuations. And then you can generalize this. In fact, there's a question in the exercises where you're asked to calculate the large deviations for any power, the integral of any power of xt, and this is a research problem. Okay, you can do the symmetrization, but the eigenvalue calculation is not so obvious. Yes, so the question is about, so here it's all about the generator. Can I do the same kind of thing using, I guess, importance sampling and change of processes? And then we'll see this in the second part of the lecture. There is a way to approach the problem by changing the process instead in order to effectively have importance sampling at the level of the fluctuations. The problem here is that, again, in order to find that change of measure, I need the spectral elements. We'll see this clearly. So in fact, the importance sampling problem has the same complexity as the spectral problem. It's the same. If you know the spectral elements, you know the change of measure, but in order to construct the change of measure, you need the spectral elements. Okay? Okay, so I think this is the end for the first part. And I'll welcome you to have a look at the notes and the exercises, especially. I think in a way, you don't learn until you do some exercises. I have a page here to say how this changes for jump processes, but I'm not going to go over this. This is something that's known, and it's also an exercise in the lecture notes. Okay, so I'll draw a line here for the first part, and then I'll jump to the second part now, which is good. We can calculate the probabilities for these fluctuations, for these rare events, and now we're trying to understand how they arise in time. And Vivien actually mentioned a few things that are related to this. So in fact, Vivien was trying to construct an effective process, a change of measure, a change of process, that is exactly what I will be talking about now. Okay, so this is lecture 2. I don't know if they'll separate this in the video. Markov processes, conditioned on large deviations. And I'll give you some references here. So this is work I've done with Raphaël Chetrit. So we had some PRL in 2013. Then there's a paper in the Annales Henri Poincaré, 2015. And most of the details, this is the long paper that has all of the details. And I'll be mentioning some new results on control theory, which comes from a Journal of Statistical Mechanics paper, 2015 too. Okay? So the problem is a conditioning problem, but I can define the problem in many different ways. And I'll just try to explain what the problem is about, and then why it's actually a conditioning problem. So again, so this is the problem. We have again a Markov process, and then we have again some observable, which will be the time-integrated observable that I mentioned before. So in terms of simulation, if I was to go to find a distribution of the observable, what I would do is to generate trajectories of my process numerically. I could simulate the SDE, and then generate one trajectory up to the time capital T, and I would calculate, so this is my trajectory 1, I would calculate the value of the observable here, and this will be like my first value. So that's the first element in my sample that I want to get for the observable. And here I would calculate the histogram that I get by repeating the experiment. So I will repeat the experiment, I have a second trajectory, I have a third one, and then after some time, after many trajectories, I have a sample, and then I can calculate the histogram of this, and I will get, okay, so this is quite smooth. Of course, the histogram won't be that smooth, but you see you have a histogram from the experiment that you do. Now, if you simulate this, most of the time, because it has an LDP, you'll get events that are close to the mean, okay, because this is exponentially likely. So most of the simulation you'll generate will be in that region, that typical region here. Now what I want to do is to say, suppose now I'm looking at some fluctuations far away from the typical value. What are the trajectories that actually generate these values? So I could go back to my simulation. Suppose I have enough sample, an exponentially large number of samples. In fact, suppose I see some of these values there. How were they created in terms of trajectory? So if I look at them, maybe I'll see something like this. So I just go back to the trajectory and I color them according to the value I want. So maybe I have something like this. So here I'm actually suggesting something. The trajectories will look different. They will look different from the typical trajectories that you have. Okay, so this will be that region here. So this set of trajectories are the trajectories with a fixed value of A. In probabilistic terms, these are the trajectories conditioned on reaching a certain value of A. So what I'm after is really, I take my process and I want only the trajectories that gives me the value ATA. So this is a conditioning. From a physical point of view, this is like a microcanonical ensemble. You're looking at a set of configurations, here trajectories, that gives you a fixed value of the energy. Here, a fixed value of the observable. So it's the same notion, but here I'm conditioning now in time. I'm conditioning at the level of a process. Okay, so this is what I want to study. I want to study that conditioning, which would tell me, of course, how the fluctuation is created, because by looking at only the path that lead there, I'm really defining a process, and that's the process that creates the fluctuation. So if I can understand that process, I really will understand how the fluctuation is created, and that's the conditioning problem. Okay, so the big question will be about this process. Now, that process is not so obvious. I can construct it, and I will show you how to construct that process in terms of a path measure. But then you have to ask yourself, is this a Markov process? This we don't know. There's some indication that this is not Markov in general, but what I'll do is that I will construct a Markov process which mimics that process in the long time limit. And then for this I would need a notion of process equivalence, and then I'll explain what I mean by this equivalence between a process which doesn't look Markovian but actually can be mimicked by a Markovian process. Okay, so that's the problem. Then at the end, if I can construct this process, then this will be a nice process to use for importance sampling, because it realizes the fluctuations with probability 1. So if I simulate that process, then I'm going to get only those fluctuations. So that's a good importance sampling. Yes. So we'll get to this. In fact, there will be three processes in the talk. There will be this condition process, there'll be a non-homogeneous Markov process, and there'll be an homogeneous Markov process, and then in the long time limit, somehow they all become equivalent. Okay, now before I go into constructing or studying this process, I want to mention that the idea of conditioning a stochastic process is not new. It's something that's been studied a lot in mathematics, and then you have this different kind of conditioning. So maybe I can just open a parenthesis here to talk about conditioning. There's a very old conditioning that dates back to Doob. Well, actually, even before I go there, we've heard actually mention of a conditioned process, which is the Brownian bridge. I think Frank actually mentioned the Brownian bridge last week. The Brownian bridge is you take the Brownian motion and you condition the Brownian motion on returning at some time t, which you can take to be the time 1, to return at 0. So this is, you look at all the paths of Brownian motions that return at 0 at time 1. Okay? So this is a conditioning of Brownian motion. And then this is actually Markovian. We know the conditioning is Markovian, exactly Markovian for any conditioning time. And we can write down the stochastic differential equation for that process. It's one which is not homogeneous. It has a drift that is time dependent. Okay, and then you can derive this. And the way you derive this is from a theory dating back to Doob, where now you can take any Markov process and then you can condition that process on hitting some set at time t. You can also condition on some random times, okay? And that's part of the theory too. So this is a general, we call it a punctual conditioning, because you take your process and then at some time t, either fixed time or random time, you want to reach some region B. Okay, but you condition only at a fixed time. So this is a punctual conditioning, and there's a whole theory for deriving the Markov process associated with the conditioning, and this is based on harmonic measures and so on. And it's very nice theory. It's not so known in physics actually, but it's complete. If you have a stochastic process, you can do the calculation. Okay, so these are punctual conditioning. There's another type of conditioning which is the Schrödinger bridge, which is a very interesting history in terms with its connection with quantum mechanics. This dates back from 1932 from work of Schrödinger, where you take n diffusions. You take n diffusions and then you condition the empirical density of the n diffusion to be some function at some time t. Okay, so you're forcing the diffusion to behave in density sense according to some fixed distribution that you want to reach at time t. And Schrödinger was looking at this to kind of derive a Markov picture of quantum mechanics, and there's also a complete theory for this, and it's been studied a lot in mathematics under the name of Schrödinger bridge. There's also a complete theory for this. You have to construct a forward process, a backward process that meet at time t, and actually generates that distribution Q. But this is also a punctual process. You're conditioning at a fixed time. The point I want to make is that the conditioning that I'll be studying is not of this kind, because I'm conditioning over the whole time horizon 0t. So I'm going to derive a process which actually runs over that time horizon, but the conditioning involves the future and the past of the process. It involves the whole time interval. So it's a different kind of process, and we couldn't find this in mathematical literature. So it's something, in fact, we'll see that the process that we get is a generalization of the Doob transform. So the bridges usually are given in terms of what we call a Doob transform, the Doob H transform. Okay? Okay, so now I'm going to start constructing that process, and I'll get to the main result, which is the equivalence of the generalized Doob process that I'll construct with the conditioning. Okay, so for this you can do for a Markov chain, for a jump process, but I'll do it again for a diffusion. We did diffusion in the first lecture, so it's just a natural continuation now to do this theory for a diffusion. So I need to define the process first, then I'll define the observable. It will be the same observable that we looked at before, this AT, this time integrated AT, and then I'll define the spectral element actually, so I'll be able to speed up a bit because we've seen all of this before. So it's going to be the same diffusion. So here I have dxt, dfxt, I have a drift dt, and again the theory can be done for a space-dependent noise, but just for the simplicity of the lecture, I'll take the sigma matrix to be constant. Okay, so I have xt, it's a vector in Rn. You could have m components of noise. M can be the same as n, but it can be different. This is a matrix n by m, and this is now a vector field that is called a drift. And again, you would have to put some conditions on the f and the sigma to make sure that you have a well-defined process. But what I want is an ergodic process. So I assume that the process is ergodic. So the choice of f and sigma is such that this makes the process ergodic. Okay, and yesterday I've mentioned, okay, what can we write about this stochastic differential equation? You can look at the evolution of the time-dependent density. And if you start from some initial condition, some initial density, you're going to have an evolution of that density that follows the Fokker-Planck equation. So I'm just writing this explicitly here with the generator, and then the generator we know the expression of, so I'm not going to write this. Or you can look, if you want, at the evolution of expectations of functionals, test function of the process. So physically I would write this physics notation with the angle brackets, and then the evolution of this in time follows the dual evolution. So the evolution here, you're acting with the generator on phi, and then you take the expectation at time t. So that's the evolution of test function, and I've explained yesterday that this follows a dual point of view according to the inner product defined with the expectation. Okay, so we know how to go from here, from there, and then the L is really the dual with respect to the Lebesgue measure of the L dagger here. Okay, so these are the 2 points of view that you can adopt in order to study the diffusion. Either you look at the time-dependent distribution, or you look at the evolution of any test function. If you can characterize that evolution at the level of any test function, you know everything about the process, more or less. Now, there's another level of description that will be very useful for us, which is the path measure. The path measure physically is, from the physics point of view, is just a probability over the path. So I would write this something like this. It's what we would use in the path integral. Okay, and then if I stretch really the maths here in a very formal way, this is just a probability distribution over the paths running over my time horizon 0t. Okay, now that distribution or density does not exist. It's just a formal object, okay, but you see what I mean. It's a kind of measure over the path. You can make this actually precise mathematically, and then in our papers we write this as a certain measure that starts with some initial condition. It's a measure over trajectories over the time t, and it's a measure for a system with generator t, okay? And then here you would have some element of the space of trajectory. Okay, so that measure actually exists in some very indirect way, because you can use that measure to write any expectations. So for instance, if I want to write expectation of the form f of xt, mathematically I can write that this is an integral over all the paths of my path measure here, and it's the f xt and then the element here. So mathematically you would write this. Now, whether you can actually display or write down what that measure is not relevant. It's just a formal notation to say that there is a measure on the path, like a sort of Wiener measure, and then you can contract it down to any expectation involving 1 point of the process, 2 points of the process, any points of the process. Okay? And Kolmogorov actually showed that this exists in a way. You can view this, if you want, as kind of, if you can look at the 1-point distribution, 2-point distribution of your process, n-point distribution, and then you let n going to infinity, then you can construct the path measure. Okay? So that measure exists in projection sense, if you want. But physically, I'll be using more or less this, okay, which has the same meaning, just for the ideas. Okay, so you see what I'm doing here. I'm just trying to characterize the process at the level of its trajectories. The process has a kind of probability distribution in a very weak sense over its trajectories. If I know this, I know everything about the process. Now for a Markov process, this measure has a nice multiplicative property. And then the question will be, if I can write down a measure like this, how do I determine that it's Markov or not? Okay, so that's the first part, the process part. The second part is the observable, so I'll be quick on this one. The observable that we consider is exactly the observable that we considered up to now. For diffusion, I have a purely time integral part, and then for doing a bit more of physics, I can also consider something that will depend on the increment, and again, I'm using the Stratanovich product for convenience. Okay, I could use the either product too. And the hypothesis that I need now for all the work is that I have an LDP for that. So AT satisfies the LDP with a certain rate function, with rate function I of A. Okay, this is the basic hypothesis of all the work, because I'm going to need this actually, that I have a large deviation principle. And what that means is that I'm conditioning on rare events that have a very specific form. I could condition on fluctuation in general and try to build a theory where the distribution of AT is any distribution. Okay, that's likely to be very difficult. Maybe, I'm not even sure you can carry this through. But what we're going to do is that now we're assuming that we have a very specific form for the distribution, the large deviation form, and now we're conditioning on rare events that have this large deviation form. So I'm conditioning on large deviations at the speed t, but you could do this also with a different speed. So the picture I have, of course, is that the distribution has the large deviation form, minus ti of a, plus corrections, if I put the equality here, plus corrections that grow smaller than linear in t. So really what you have again is that picture where you have the dominant behavior as the exponential, the decaying exponential. And again, I'll just repeat the picture to make this clear. What I have is that the rate function in general, the rate function is always positive. In many cases it is convex. You have 1, 0 corresponding to the mean, and the mean is also the concentration point of the observable, and that's the law of large numbers. So if you look at a specific time, you have a distribution like this. For a longer time, you see the distribution concentrating around that mean, and then for a very long time, it becomes really peaked, exponentially peaked around the mean. So as AT, the time goes to infinity, the running average of this is the ergodic mean, it converges to the mean. Okay, so that's the law of large number. If you look at the rate function, in many cases, it's quadratic around the minimum, so you could say that you have Gaussian fluctuations around the concentration point, around the law of large number, but far away, it might not be quadratic. You could have a linear part here, and the linear part will tell you that the large fluctuations are exponential and not Gaussian. So it goes beyond the central limit theorem by giving you more precise information about the tails of the distribution. Okay, hence the name large deviations. Okay, so that's the picture. We're conditioning on the large deviation event. Okay, so now I'm going to define the condition process, and then I'll get to the main result. Okay, so the condition process is just what I've erased there, actually. So I'm going to put that picture again. So just as a notation, this is not a definition, but the condition process, as I explained, is that you take your process and you condition it on some value. Okay, mathematically, this is also with physicist style. Of course, mathematically, what you would do is that you would say a condition for the random variable to be part of a set B. So you condition on a rare event. You could condition, for instance, for AT to be smaller than some threshold value alpha. But just to make the ideas clearer, I'm just going to say, okay, I want to condition on some kind of precise event. It could be just like a small box A plus delta t if you want. It doesn't really matter. Okay, so how do I define this now in terms of probability, in terms of stochastic process? What I'm going to do is to use the path measure. So I'm going to say, I'm going to define the condition process as a condition path measure. So this is just the path measure of a trajectory condition on having a given value. Okay, so I'm just conditioning in the usual sense the path measure. Yes? No, the path measure you can write down really just as a formal object for any process, not even a Markov process. Okay, and that path measure only exists in terms of projection, like this. So, okay, so of course to calculate the expectation here, I only need the distribution at time t. Okay, so what I'm writing essentially is just a formal writing where I say, well, no, it's the expectation over all path for all the elements of my space, for all the possible realization of my process, but only the function only depends on the time. Okay? Yes, exactly, and that's the Kolmogorov construction. Okay, and then you can do this. I'm not sure. It's like any process, even processes behaving badly, of course, the bad behavior will arise at the level of expectations, any kind of endpoint expectations. But presumably you can get this endpoint distribution by projection of the path measure. I think they might be, they should be conditioned. It's something like to look at on the side of Kolmogorov, okay? But essentially But again, this object, I cannot write down what this object is, although we do in physics, but that's a different question, okay? But this object does not really exist explicitly. It's just a kind of intermediate object, like a super object. I mean, it's the most refined object you can write down that characterizes the process, but that object does not exist as such. It exists only via projections. But since you can do this for any projections, you imagine that this object exists. Essentially what Kolmogorov proved is that, so that object exists only via any kind of projections, but what he proved is that this object is really unique if you lift it to the finest projection ever, okay? For me, it's not so much important that this object exists, because you'll see, in fact, that the result, the way we prove the result is by calculating random Nicodim derivatives. So I don't need to play with this object. I only need the ratio of this object with another measure, and that always exists. The comparison of a path measure to another path measure always exists. That's the random Nicodim derivative if you're comparing two continuous, absolutely continuous processes, which is going to be the case here. So I have an explicit expression for the random Nicodim derivative, and that's all I need. So in fact, for the theory, I don't need to show what the expression of this guy is. Okay, let's go back to the condition process. So the idea is that you look at a pathwise conditioning. This is the idea. So if I use a definition of the conditioning, I look at all the paths x, the probability of certain x, and that path leads to my fluctuation, and I just divide by the probability of this. And if I reverse this using Bayes' rule, what I find is I have the probability, the original probability of x. I'm going to have the constraint that AT is equal to A divided, I'm going to put the normalization here. Okay? So this is just using Bayes to rewrite the conditioning in this sense. But what you see is that the condition process is only a reweighting of the original path process. You look at all the trajectory, the probabilities, and then this will be equal to 1, say, if the trajectory has the value AT equals to A, and otherwise it's 0. So you're just reweighting all trajectories. You just put your weight over all the trajectories that give you that fluctuation and 0 weight for the other ones. Okay, that's the idea. And again, you can make this precise using the path measure. Here I'm using just the physicist notation to give you the idea. But from this, you see that you have the microcanonical ensemble. When you define the microcanonical ensemble, you do exactly the same thing. Here you have the probability of the configuration equal to something, and it's equal to something else. It's equal to 0 when you don't have the constraint. So this is only the microcanonical constraint. And that constraint defines the measure here. Okay? So in terms of path, what I had, again, is that if I have a trajectory that doesn't have A, it's got 0 measure. But if I have now another trajectory that has 0, that AT equals A, this one has the original path up to some constant, which is a normalization constant. That's the normalization constant. Okay? So now, this is a process because I'm defining a measure over the trajectory. So this defines a process. Now the question is, what is this process? Is this a Markov process? Presumably no. It's very difficult to see because you have that constraint. If you start with a Markov process, this is a Markov measure, but the constraint actually kills the Markov property. So it's a very difficult process to look at. If you simulate this, this is very difficult and inefficient too. You could say, I can generate a trajectory. What I'll do is that I'll just simulate the trajectory. I'm not going to show it to you if it doesn't have the constraint. Okay, so let's do this. If you do this, you're going to wait an exponentially long time before you can see such a trajectory because it's a rare event. So to see such a trajectory, you have to actually simulate an exponential number of samples. Okay, but it's a process. If you limit only those trajectories, you have a certain process. Huh? I think it's a Markov process for some observables, but it's not a Markov process for every observable. Then you can, it's something we could discuss later on, but if you do a conditional limit theorem, if you project that measure, then it will be Markov. But the global measure over the trajectory is not necessarily Markov. Yeah. Okay, so what I'm going to do is that I'm going to define another process, which will be Markov, and I will show in the end that it's asymptotically equivalent to that process. So this all depends on T, of course. And what I'll show is that the PA is very close to another process, which I'll construct, and this one is Markov, and this will be true when T goes to infinity. Yes? Yes, but think about the bridge. You could say the same thing about the Brownian bridge, but funnily, the Brownian bridge is Markov for any time. And if I use a particular observable which is punctual, suppose I choose AT to be really just a punctual conditioning, then I have a bridge which I know is Markovian. So you're right. I mean, that's essentially the idea. If I change time and I change the value, somehow all the paths have to change, so that looks non-Markovian. But there are some observables that lead to a Markovian process. In general, it's very difficult to think about what this process looks like. Okay, so now, from now on, what I'll do is to construct this process, which we call the Generalized Doob process, or the auxiliary process. Vivien called it the auxiliary process. It's exactly the same process that he discussed yesterday. And for this, I need a spectral element, and then I'll be using what I was talking yesterday. And I can speed up a bit here. I have 14 minutes. I think we'll be fine with time. So I need the scale cumulative generating function. So this is what I was saying before. That process will be built from the large deviation elements. So building that process is as difficult as finding the large deviation. So the first one I need is this. This is the exact same quantity that I defined yesterday. And this, we know for Markov process under some condition, is the dominant eigenvalue of some tilted generator. Then by Gartner-Ellis, I have the rate function under some conditions as the Legendre transform of the lambda k. The tilted generator, we know again, but I'm gonna put the explicit expression is f plus kg plus 1/2 kg d. D is my sigma transpose. Kg plus kf. So that's the generator of the Feynman-Katz semigroup. It's a generator of the Feynman-Katz equation, like I discussed yesterday. And the spectral problem that I need to solve for the dominant eigenvalue, spectral problem for the principal eigenvalue, is the problem where I'm acting with Lk. I need to find the dominant eigenfunction associated with the dominant eigenvalue, which I'm writing here, the zeta max. Okay? Okay, so for the construction, I need those elements. So in a sense, I need to solve the large deviation problem first, and then I can construct that process to understand how the large deviations are created. Then we can talk later on about whether we can do this without solving the large deviation problem. It's a kind of a egg-chicken problem. Okay, but there's some things we can do here. Okay, so here's the construction now for the driven, we call this the driven process. It's got other names. So Vivien called it the auxiliary. We also have the name effective process, or the modified process, because it's an effective process. It's a modification of the original process that tells you how the fluctuations are produced in an effective way. Okay. So it's a process, I'm going to call it X hat, and the generator of that process is the following. I'm going to write the generator now LK, but just L capital. It's a different LK here. I'm using the script LK. I'm using the script here because this is not a Markov. It's a Markov generator, but it doesn't conserve probability because it's the generator of the Feynman-Katz semigroup. So that's for the generating function. Here, I'm really writing a Markov generator. So the explicit construction is that you take RK on one side, you apply this like this, and then minus here, minus 1, RK, lambda K. Okay, and this is like the symmetrization. This is an operator sense. If I apply this onto a test function, say h, the meaning of this is that if I say this will be a function after I apply it, this is the function that has, this is just a constant here. Here I'm going to apply the tilted over the product. Okay, so this is an operator sense. And this is only a sort of diagonal constant part that doesn't play any role, except for the normalization. So I'm going to have, and then here the function. So here I'm going to have x. Okay, so you see the meaning of this generator. It's quite easy to show that this is a Markov. It's a conserving generator, so it conserves probability, because if you apply this onto the constant function, you get 0, so that's the property of conservation. So it's Markov. Again? No, it's the, because if I apply this on 1, here I'm going to have a lambda 2, right? This will give me lambda. So I need 0. So LK applied to 1 is equal to 0. Yeah, this is a scalar. Oh no, yeah, it's a function. So this will be 0 times, say again, the constant function. This is the 1 is the constant function. It's not the. This is a function, right? Yeah. Yeah, but no, I'm not sure I understand. This is just like a diagonal part that's not acting on the function. Yeah. Oh, no, sorry. You're right. Yes, this is actually like this. Because what I had here, in fact, in my notes is RK minus 1, LK RK. So this gives me the lambda K. Yeah, sorry. And then this cancels this one. Sorry, yes. Yes. So for k equals 0, we know that, okay, that's a good property. For k equals 0, we know that Rk is equal to 1. It's a constant function. And then the tilted is also equal to L, so you're not changing the process. Yes, exactly. I'm using like kind of transpose convention compared to what we're using in physics. So in fact, what what Vivien yesterday was calling the left and the right eigenvector. For me, it's okay. Yes, we'll discuss this later on. The splitting is an algorithm for generating the Feynman-Kat semigroup. So it's an algorithm for generating the generating function. Okay. Whereas what I'm going to present is more like an importance sampling scheme at the level of the process. I'm simulating the process itself, not the generating function. Okay, and I'm showing a different process that will generate the fluctuation. So I'm not talking about generating functions. It's a kind of complementary picture over the fluctuations. Okay, so I have this property. It's a Markov generator, so this is a Markov process. It's got, for k equals 0, it's the original process, so you're not changing it. But what's more important is that I have an explicit expression between the path measure of that process and the original measure of that process. And this is really important. Okay, so if I start with an initial distribution, this is the process of generator Lk for time t, I can calculate the random-Nikodym derivative between that process and the original process. And this is what answers the question of Nico, is that this is what I need, and this is explicit. This is equal to Rxt, Rx0, and here I have the exponential t k at minus lambda k. So this is not so difficult to prove. This is the explicit random-Nikodym derivative between this new process x at versus the original process that you had xt. Okay? So this is quite general for diffusions. I cannot explicitly write down a measure for the driven process or a measure for the original process. That path measure only exists in some implicit sense by projections. But I can write down the comparison, the ratio of the two path measure. And then when you play with stochastic processes, that's all you need. Okay, then we call this a general Doob transform because if you looked at punctual conditioning, that construction is the Doob construction. The R essentially will be a harmonic function, the lambda will be equal to 0, so you're really doing a punctual conditioning of your process. Okay? So that's a new process. What I want to show now is that that x hat is somewhat related to the conditioning. This one here. It's not that process. If you look at the fluctuations of AT, if you look at AT with respect to x hat, it's not equal to A with probability 1. So it's not exactly the conditioning. But we'll show that it's very close to the conditioning. Okay, so that's the main result here. Okay, so there's some hypothesis. So there was one which AT has LDP. I've mentioned this. I need also I of A to be convex, and this is really important. And then also I need the spectral element to be somewhat regular. So there's one condition that if you choose an initial condition, the R of K has to be finite. And there's some more technical conditions like this on the spectral element, which I'm not going to write, but these are sort of minor hypotheses in the problem. They're just technical hypotheses about the spectral problem. The main one really is that I have an LDP with a convex rate function. And convexity is really important. We understand why you wouldn't have what I'm going to write down if you don't have a convex rate function. But like we discussed yesterday, in any case, we think that all rate functions of Markov observables are convex. Okay, so it doesn't seem like a big problem. So the result is the following. I'm going to write the result in different ways, just as a kind of table, and then I will explain what I mean by this result. So we started with the condition, right? So we had the process and the condition. We don't know much about this process. And here we have the driven on the other side. And then I have an explicit construction for that process. In fact, I know that this process is also homogeneous, right? I should write this down here. That process is not time dependent, it's time independent, so it's homogeneous. It's a homogeneous Markov process. The result that we can prove is that we have equivalence in the long time limit. Now here I'm not saying anything, I'm just writing down something just in math sense, okay? And then I will explain what I mean by asymptotic equivalence. So here we have what we call asymptotic. Again?
Would this new change in measure be obtained from Gaussian theorem?
Yes, yes. So here, in fact, how we get this result is we can write down Gersanov for this, and this is what we get. And also with Gersanov, then I can write the new drift for the generalized Doob process, and I'll do this in a minute. Okay. So the main point is that we have the condition process, we have the Doob there, and then we can show that these are asymptotically equivalent in the long time limit. Okay, what do I mean now by asymptotic equivalence? So there are two meanings of this equivalence. And there are, in fact, these two interpretations are equivalent also. Okay, there's a first one. So this is the meaning. So we say asymptotically equivalent. So there's the first meaning, so the meaning of equivalence, and this is what we can prove. The first one is that if you look at the log of the random-Nikodym derivative between the condition and the driven, so this is for all elements of my space, this goes to 0 in the long time limit for almost, or actually PA or P driven almost everywhere. Okay, so the two processes are different, but if you look at the random-Nikodym derivative, it will scale like time, but the differences somehow are sub-exponential. So in kind of informal notation, you would say that the condition process is, in a large deviation sense, the same as the driven process over the exponential scale. Okay? In the sense is like you have only small OT difference in time almost everywhere. So the two path measures are different, but the difference are sub-exponential in time. There's a problem with, so the support of PA is smaller than the support of the driven there, but where this diverges actually as measure 0 in the long time limit. Okay, so you have the same concentration properties, and then you can show this. Yes? Yes. K, yeah, actually it's in my notes here. K has to be the K that you choose in the Legendre transform. If I want the fluctuation A, I'm going to choose K to be the derivative like you choose in the Legendre transform. So this is, I choose the temperature to be the derivative of the entropy. Okay? And this is where you need the convexity. If you have a non-convex rate function, you cannot do this. In fact, the general result is that K has to be part of the subdifferential of I of A at the point A. If I of A is not convex, it has no subdifferential. Okay, so this is only if I of A convex. So this is where you need the convexity property. So you have equivalence only at points A where you have local convexity. Yeah, so this is, I'm writing this if you have a differential rate function, but otherwise this is what you have to write if I of A is not differentiable, but convex still. Okay, so that's the first meaning. You see what I mean, is that you have two different path distribution, they're not the same, but they differ in general by a term which scales exponentially, but not linearly in the exponent. So when you take that limit, for almost all trajectories, you see more or less the same path measure. And this is sufficient to get the same large deviation. So this is the second meaning of equivalence. No, actually, before I get to that meaning, this is the same too of having, if you look at the relative entropy between PA and P driven, this also goes to 0. Okay, so in relative entropy sense, in relative entropy rate sense, they're the same process. And the third one is that if I look at another observable and I see that it concentrates with respect to the condition measured to some point B star, then the equivalence implies that with respect to the driven process, it will concentrate on the same point. Okay, so here I'm not writing everything. The idea is that if I have another observable, not the conditioning observable, but any other observable that has an LDP with respect to the conditioning, and I see that this concentrates on a certain B star, then I'm going to have the same concentration on the same point with respect to the driven. So although the two path measures are different, they concentrate in terms of observables on the same points. Okay, and this can be proved precisely. So this is the meaning of equivalence. So again, two different processes, but they look the same in the long time limit in Radon-Nikodym sense, relative entropy sense, or concentration sense. In general, the fluctuations of BT will be different in the two processes, but they're going to have the same concentration points. And this is it's a good equivalence. It's actually the same equivalence that we have in statistical mechanics, in equilibrium statistical mechanics. In fact, what you can imagine, and I've mentioned this already, this is like the microcanonical ensemble. You look at all configuration with a fixed energy. Then this will be the equilibrium states in that ensemble. This is like the canonical ensemble. You're fixing the temperature instead. You're fixing K. And here you can have equilibrium states in the canonical ensemble. And so what you're saying here is that the canonical equilibrium states are the same as the microcanonical equilibrium states. In general, we know that the fluctuations of microcanonical are not the same as the fluctuations of canonical, but they have the same equilibrium states. And that's enough for us. And here it's exactly the same thing. In fact, the proof of all these results follow exactly what we know in terms of equilibrium equivalence of ensembles. Because after all, these are really just ensembles, microcanonical and canonical, but defined over trajectories instead of fixed configurations. Okay, so I have 15 minutes now. So what I'm going to do is I'll give you an idea of the proof, and then I'll do just two simple examples related to the Ornstein-Uhlenbeck process, okay, and relate that to the large deviation calculations that we've done. So the idea of the proof is all based on equivalence, and I've given more or less the idea is the idea that you want to compare the canonical and the microcanonical ensemble. You know that these ensembles are equivalent, and so you want to discuss that equivalence. So the idea of the proof is the following. So again, I'm going to just put a kind of table here. So you have the conditioned here, that's the microcanonical. That's the process here, condition with the hard constraint that you have the fluctuations. I think I'm losing the microphone here. Yeah. After an hour, it moves. That's good. Thank you. Okay, and I want to compare this with the driven here, the Doob, okay, which is homogeneous. And I know that process, but I cannot compare that process. So that's the driven. That's the driven process here. Here I have the path measure, PA, which is the conditioning, whereas here I have the path measure, the driven process here, with a certain K, right? Okay, we don't know how to compare these two processes directly. What we're going to use is something in between, which we call the canonical, which is just the exponential tilting of my original process. This is an exponential tilting. We call it the canonical because it's going to canonical form. Okay, so it's the exponential family of your original process. This also defines a process, and we know a lot more about this process than this one. This is Markov, but time inhomogeneous. We can write down the generator, and what we can show is that we have asymptotic equivalence between these two, because I can write the random-Nikodym derivative explicitly between the p-driven and this one. This is good. Okay, and this works really just as an equivalence of Markov processes. And although this one is non-homogeneous in time, as time goes to infinity, it becomes more and more homogeneous. So it converges in time to a homogeneous process, which is the Doob process. And that what we knew before, actually, from studies of equivalence, is that I also have equivalence on this side. I have asymptotic equivalence in the same sense as here between now the microcanonical and the canonical. And so if I have asymptotic equivalence between the two here and individually between the two here, it also means that I have asymptotic equivalence between the driven and the condition. Okay, so that's the idea of the proof. And it's all about playing with random-Nikodym derivatives. I never play with the path measure individually. Okay, I'm writing this now, but it's only to give you the idea. Everything is based on the comparison of processes. And this is how you can actually make this rigorous mathematically. Okay? Okay, so that's the idea. Now what I want to do for the last 15 minutes is to do some examples. And before I do this, I'll just write down what is the effect of the Doob transform onto the original process. So I'm going to write down explicitly what the driven diffusion is. So remember that I start with my original process, which has a stochastic differential equation given by a certain drift capital F plus a certain matrix for the noise, sigma. Since I know the random-Nikodym derivative explicitly, from Gersanov, I can go back to the stochastic differential equation for the driven Doob. Yes? If the diffusion matrix. T. We haven't done that. I don't know. I think you can do large deviation for the random time, but the random time still has to go to infinity in order to still have a large deviation. So there might be something you can do with random times, but you would have to sort of control how the random time goes. Also, you need some distribution for the random time, but yes, it will be. We haven't done it, so I don't know if you can do it or if you have the same kind of equivalence. Yeah. Okay, so the driven process also have a stochastic differential equation. It modifies the drift, so I'm going to call it Fk because it's all parameterized by k, and it doesn't change the noise. It only changes the drift. So the two diffusions we say are absolutely continuous. So that comes actually from Gersanov. Because I have the random-Nikodym derivative explicitly, it doesn't change the noise. If it changed the noise, I could not actually compare the two processes. Okay. And so only the drift changes, and the drift is given explicitly by this formula. It's an additive perturbation of the original drift, where you put the D matrix, Kg, plus the gradient of log Rk. If you don't have any G, then it's just a gradient perturbation of your original drift, and this is a result that was floating around for quite some time in control theory, stochastic control theory, also in terms of importance sampling, optimal importance sampling. The new thing, I guess, in physics is that if you put now in your observable a G part, then this is what you get. And you see now that this is not a gradient perturbation, and this ties with the question of François, is that when I have a non-gradient G, you see I'm changing the process in a way that is not gradient. So if I start with a gradient system, I'm going to have a non-gradient perturbation. So now the effective process, the Doob process, won't be reversible. Okay, so it's all here. Again? Yes. So what is this process? This process is the optimal change of measure. It's the one that has asymptotic zero variance. That's the conditioned. That's the conditioned process, but we don't know anything about that conditioned process. So this one has exact zero variance. We don't know much about it, but we know it's asymptotically equivalent to this one. See, it's clear that the two processes are different because on this side, I have AT equals to A with probability 1. What do I have on this side? I don't have this property. The property that I have is that this in the long time limit will concentrate onto that constraint. So here I have a soft constraint, which is the canonical ensemble, and then it only concentrates in the long time limit, whereas here I have the hard constraint. So here you have zero variance, but here you have asymptotic zero variance. Yeah, I don't know, but okay. Okay, so I have the process explicitly. So you see now, to construct that process, I need a spectral element. I have RK, and what is the dependence? I have an explicit dependence on G. There's also a dependence on F via the eigenfunction, of course. Okay. So let's have a look at a few examples. I'll start with Brownian motion, then I'll move on to Ornstein-Uhlenbeck. I think I have enough time. The first one is, examples. First example is Brownian motion. I want to condition Brownian motion, so Brownian motion. I want to condition Brownian motion to reach a certain point in time. So that's a bit like Doob. So I'm going to take a Brownian motion, and I want that Brownian motion to have a position which grows with time. Okay, so that's actually a Doob type conditioning, but it also has a large deviation flavor to it because I want to do this now. I want to go far away with time for the conditioning. So I'm pushing the conditioning here. Usually Brownian motion will have trajectories that follow square root of t. What I want is something that actually grows like t. So if I fix t here, I want here a t. In a way, it's like having a Brownian motion that has now a fixed velocity. Okay. So this is a large deviation event because, in fact, again, the position usually grows like square root of t, so I'm going away from that typical region, and there's a large deviation event, there's a large deviation principle ruling that probability. So you can see this also in the sense that the WAT, so my observable in this case is 1 over t, integral of the Brownian motion is equal to a. Okay, so what do I have here? I have f equals 0, and I have g equals 1. I can do all the calculation, blah, blah, blah. And what you get is that the conditioning on W now, it's not x, WT is equal A, is asymptotically equivalent to drifted Brownian motion. Okay, which is sort of expected. I want trajectories that shoot far away linearly with A, so they have mean speed A. So the expectation is that you'll add a drift to the process, and indeed this is what you get from the calculation. This is also what you get from Doob. And in fact, here the result is actually stronger than what we have here, because Doob is exactly Markovian at all time. So it's not even asymptotic equivalence, it's an exact equivalence in this case. Okay, so this is a case where the conditioning is exactly Markov, and then we can say something about this. Okay, that's for Brownian motion, and I'll finish with Ornstein-Uhlenbeck. So here I'm not showing the calculation, but you would have to calculate the rate function, the lambda k, the corresponding eigenfunction. You put this into this result there, and then what you realize is that it's just an added drift. Okay, so the f here originally is 0 because you're dealing with normal Brownian motion, so the capital F is 0. You're not going to have any, you have a G part, you're going to have this too, so here you have actually two sides to the problem. But it really simplifies a lot, and then at the end it's just an added drift. Other example, Ornstein-Uhlenbeck. I start again with my process, linear process in one dimension. And now I can condition on different observables, but let's use the observables that we were dealing with before. So I can condition here on the area. So I've done the calculation. I have Rk, I have the eigenvalue, I have the rate function and everything. So I can do the calculation, and what you realize is that the modified force for the fluctuation, so for my Ka here is really I prime of A, that's the K that you have to choose to fix the fluctuation, is the original one plus gamma A. So here again you have an added drift. And this you could have guessed too before, because if you want a bigger area, what you want to do is to shift the process a bit upwards. So you change the fixed point of the Ornstein-Uhlenbeck process, you just move the quadratic potential of the Ornstein-Uhlenbeck process to be higher, and then you're going to have more area asymptotically. Okay, so that's for the area. You can do the same calculation also for the area squared. In this case, actually, the rate function looks like this. This is I of A for the... This is a kind of empirical variance. Okay, so here you can do the same calculation. Again, I'm not showing the calculation. You have to calculate Rk, but this is the ground state of the quantum harmonic oscillator after symmetrization. The eigenvalue is the ground state of the quantum harmonic oscillator, but shifted. And here, the Fka is the original drift, and then you do the sum, but what you get is... Do I have the calculation? Yes. It's minus sigma squared over 2ax. Okay, which is quite interesting. So here, the conditioning only adds a drift. So you stay, it's still an Ornstein-Uhlenbeck process with an added drift. Here, the conditioning gives you another Ornstein-Uhlenbeck process with a different friction. Okay, which makes sense too, because we know that in the original Ornstein-Uhlenbeck, the variance is determined by gamma. So if you want to change the empirical variance, just change the Ornstein-Uhlenbeck at the level of the friction. Okay, so you could guess that, but again, you have to go through the calculation to realize this. Okay, so Ornstein-Uhlenbeck. In general, that's not the case. If you look at other observable, then you get a new process which is not of the same kind that you started with. And okay, so I think I'll stop here. I can write down other application. People have looked at application of that theory of driven processes to jump processes, Markov chains. There's been a lot, for instance, on conditioning, symmetric exclusion process, or conditioning zero range process on current or density. And what you get in those cases is another n particle dynamics, which is usually very different from the original dynamics. But the calculation is always the same. You need to do the spectral calculation to get the eigenvector, the eigenfunction, and the eigenvalue. And so the difficulty of finding that driven process is the difficulty of solving the spectral problem, you see? And then it's the same thing also for the importance sampling. I could approach this as an optimal change of process that gives me asymptotic zero variance, but it's the same thing. The optimal change of measure is the change of measure suggested by large deviation, which involves again the spectral problem. So it's quite difficult. Yes, maybe I have another slide about the reversibility properties, but I think you see it here. If I start with reversible, I can end up with a driven process that's not reversible for certain observables. Although, if I have no G part but only F, if I start with reversible, I still have a reversible process. So fluctuations that are only purely time additive won't change the reversibility of my process. And that relates to the spectral problem I was mentioning this morning, like when I started. What is the nature of the large deviation problem? It's all determined by the driven process, in fact. Okay. There are other results. You can view also the driven process as an optimal control process. You can write down a kind of representation formula for the process, and the solution of that representation, that variational formula, which is in fact an optimal control formula, is the driven process. So the driven process is also given by a sort of Bellman type equation, Hamilton-Jacobi-Bellman equation. and you can solve it using dynamic programming or all the techniques that you have in optimal stochastic control, but it's as difficult as the spectral problem, as the importance sampling problem. Okay, so it's all related, and there's no free lunch in any of these methods. And I think I'll stop here. Thank you.
Is there any question?
Okay, so that's the research problem. So we don't know actually. We believe that any power greater than 2 doesn't give you a large deviation at the speed t, but it gives you a large deviation at a different speed. But we don't know what is the large deviation, and then we don't know exactly what's the speed. So that's an exercise in the lecture notes, and it's rated 40, research problem.
So in the situation where you have non-strictly convex weight function, so imagine you have different values of A, which give the same lambda of k.
Mm-hmm.
Does it mean that if you condition the original process to taking all these values of A in the large t limit, they are equivalent process?
Yeah. So the question has to do, suppose I have a rate function like this. I have a rate function maybe, and I have a linear path maybe between 2 values of A. A1, A2. Now for all the strictly convex part, there's going to be only one temperature that gives you the driven process, and then the process will converge to that value. And then up to here, there will be a driven process, and up to here, there will be a driven process. In fact, it will be the same driven process because they have the same slope here. And the question is, how do you go in that region here? What you'll do is that you'll just mix the 2 processes. You'll take this, well, in fact, no. So in this case, the process is the same at the 2 points. So how do you extrapolate between the 2 values? And this will be the initial and the final conditions that will enable you to go into that region. So in order to go into that region, somehow it's funny because if you look at the point here, A, the subdifferential of A is just that point, is the slope. So all these point A's have the same slope, so they have the same driven process. So you're asking, but how can you reach different values of A with the same process? You can't. Okay, but this, you'll be able to do this by changing the initial and the final condition, but you don't know how to do this. It's not given by the theory. Yes. So we have a case like this where you condition drifted Brownian motion on the occupation. Then you have a linear path in the rate function like this. And then if you look at the simulation, this is indeed, the fluctuations here in that part are really given by a sort of boundary contribution and not by the bulk contribution, which doesn't change anyway.
So for this one, you actually need I of A, right? The rate function beforehand. But suppose you do not know it exactly. Can you recursively do it like bit by bit?
Mm-hmm. So Vivien presented what algorithm when he is doing this. So he's constructing iteratively that process. You can do this with or without feedback, and with feedback it's actually quicker. So there's a way to start. You can have a guess for your process, and then you do some sampling, then you use that sampling to feed back on the change of the drift, and then you continue, and then hopefully you can converge. And then Sandeep Juneja has worked on this a lot, but in the context of the optimal control process. But it's really related. There's also some papers of yours on the adaptive importance sampling, and that ties in with this. So there are adaptive algorithms to hit that. And in fact, it has to be this way. I mean, there's lots of work on this, and then you access that whole body of work when you see the problem as an optimal control problem. When you write down the driven process using the Hamilton-Jacobi-Bellman equation, dynamic programming, optimal stochastic control, then you just open the door to a huge body of work that can help you to find the large deviations and then try to construct that driven process numerically, iteratively. So there's lots of work on adaptive control and that adaptive optimal control. Okay, and it's our responsibility to go and read that and then implement it and not reinvent the wheel all the time to get these large deviations. And it will be to our advantage to do this. There are other ways. So maybe actually these control methods will be useful to solve the spectral problem itself. And so you can, depending on how you approach the problem, you can sort of mix the techniques and then solve different sides of the problem. You have the pure large deviation problem, which has to do with the spectral problem, or you have the simulation importance sampling problem, which has to do with constructing that process. And they're all related, of course, and then you can approach it using different sides.
So I have a general question now. Which are like challenges for the future in this area?
The challenges. So we've been working a lot on illustrating the theory for specific processes. I guess one question would be the random time version of this. This will be quite interesting. Now, all the examples we have for the diffusions are the low-dimensional diffusions, like even one dimension, but we haven't started on 2-dimension and higher dimension. This is much more difficult, also because the spectral problem is just so much more difficult. If you're starting with a non-reversible process in 2D, in order to get the eigenfunctions, again, you need to solve the 2 spectral problems, not just one. A lot of work has been done on the n-particle dynamics, conditioning on current and occupation. There's been some work on this, but it's quite challenging too. But it has to do with the spectral problem. And then the numerical side of it is also for us to do for the large deviations application. Again, there's been lots of application on the control side. Now, there's lots of work to be done to transfer that knowledge over to simulation and compare the techniques, the simulation techniques, with other techniques that we've been using, like cloning, particle splitting, and things like this. Then I guess like the major question, and it's something that Sandeep was mentioning, is what about the condition process itself? Like, can we just peek into it a bit more and then try to understand what that process is? I'm not so optimistic myself, except for specific observables like this one, where you can show that this is Markov. It could be, yes. But even for a Markov chain, we can do the same theory for Markov chains, with discrete time observables integrated in discrete time. And even that is not obvious, unless you have a punctual type of conditioning, because in this case you can use Doob. And Doob tells you that this is Markov for all time. But beyond this, it's really difficult. For instance, if you condition on the empirical distribution, it seems clear that it's not Markov. Because again, if you increase time a bit, you have to reshuffle everything in order to get the same fluctuations. And for this to be Markovian will be quite surprising to me. Okay, but I'm open to be surprised. I like to be surprised.
So you started this with an example of the Brownian bridge, which had a conditioning at terminal time. And then you extended that to the Schrödinger bridge, which was a density at terminal time.
Yeah.
And then you said that these conditionings did not fit that.
Yes.
Is it possible to do a level 2 large deviations, which is one of, you look at occupancy across time, and then these conditionings are then a terminal time conditioning of the level 2 large deviations, because these can be viewed as expectations of the level 2 measure.
Yes, but even the level 2 measure is a time integrated, no? Because the level 2 is about the time integrated, so it's not a fixed time measure. You'd have something like this. So you're still looking over the whole time horizon. You could condition on level 2, but I think, and then contract possibly to any AT, but I don't think it will be a conditional punctual conditioning.
Showing the level 2 may be a technical challenge,
Yeah.
Quite a bit of a technical challenge, but I'm just trying to see if this conditioning could be embedded within a terminal time conditioning, provided the level 2 is available.
I'm not so sure. I think one approach that we thought could work is that if you look at xt and then you condition on at, this looks to be non-Markovian. But what you could do instead is that, just look at xt and at as a couple, then this is Markovian. Okay? So you do this, and then you can condition. It seems like if you condition on like this, you condition like a bridge. But the problem is that, okay, this is Markovian. If you look at it as a couple, it's Markovian, and you can condition this. This is a Doob conditioning. The problem is that then I want to marginalize over AT in order to get the dynamics of XT itself, and it's that marginalization that we cannot do. And it seems that maybe when you marginalize, then you actually get something which is not Markovian. Okay, so it's as difficult, and then we couldn't get through just by looking. It seems like a good idea to start with, but then you get stuck. For physicists, it's like, I'm looking at the dynamics of this is Markovian, I want to trace out the AT. Is the tracing out also Markovian? We don't know.
When you speak of the conditioned process, do you mean the process on the final time, or do you mean for a fixed running time and what it looks like at intermediate times?
No, so the conditioning is for the whole time horizon. What I derive for this is a process that will run homogeneously in time. Okay, so the conditioned process is because you just constrain all the trajectories. So I'm specifying a process over the whole time 0 capital T.
Okay.
So it's running over all the
T is
time.
fixed, and you're looking at how that thing behaves in between.
It's the same, like, think about the Brownian bridge, right? I condition the whole process over the final time, but I'm defining a process in the meantime, which is defined there.
Okay.
Yeah. There was a question. There's a question at the front. Yeah, that's fine.
So you define the driven process using the symmetrization with the right eigenvector. And I remember in one of the appendix of the J-state paper, you also define another symmetrization with respect to a vector which depends on the time t and which is not homogeneous. So
yeah.
This process is equivalent to which one? And
that's the canonical. So the exponential tilting of the original process is a Markov, but time dependent, and it's that process. So the Doob transform is actually a time dependent generalized Doob transform in that case. But in a long time limit, it becomes homogeneous, and that it gives the driven process, which is a homogeneous process. In a sense, it's a bit more subtle than this, and I think, Vivien, you know how it works, but essentially you have 0t, and then the canonical, the tilting is actually Markovian, but not homogeneous over time t. But as you increase t, then there's only like a part here that is the time dependence. The bulk becomes homogeneous. So as t goes to infinity, if you squeeze it down now to an interval 0, 1, you're just squashing the time dependence at the boundary. And this is why your final density is not the same as the bulk density.
So I was just thinking, like, as a practical tool, I mean, supposing I want to use it, I have a second observable B, and I want to find its statistics conditioned on some value of A. So then I guess this is this a useful method?
Yeah, so then simulate the driven process for any other observables. And these are if you get concentration points, these are the concentration given the fluctuations. Yeah, so it's not only good for AT, but it's good for anything else after, yeah.